In previous lecture, we introduced limit superior and limit inferior as tools for studying sequence that fail to converge. But today we will discover something surprising. Some ideas actually give us a completely new way to understand convergence in itself. Last time we look at this sequence, -1 to nth power. This sequence keeps jumping back and forth forever, so it never settles down to a single value. In other words, it does not converge, but something interesting happened. Even though the sequence failed to converge, we were still able to describe its long-term behavior using limit superior and limit inferior. In this case, the upper behavior stay near 1, while the lower behavior stay near -1. So now a natural question appears. What happens if the sequence actually does converge? Will the upper and lower behavior eventually become the same? Now let's make a guess. Suppose the sequence actually converges. That means the sequence eventually settles down near some number x. So intuitively, the oscillation should disappear. The upper behavior and lower behavior should no longer stay separated. Instead, they should collapse into the same value. In other words, maybe lim sup equal lim inf equal x. And today we are going to prove that this intuition is actually correct. Let's test this idea on a very simple example. Consider a sequence 1 over n. We already know this sequence converges to 0. So now let's see what happened to the tail supremum. Remember, the tail supremum means if we start farther and farther out in the sequence, what is the largest value we can still see? But this sequence is decreasing, 1 over n greater than 1 over plus n and greater than 1 and so on. So the largest value in the tail is always just the first term. Since the sequence is decreasing, every tail looks like this: 1 over n, 1 over n plus 1, and so on. And because the sequence keeps getting smaller, the biggest value in the tail is always the very first term. So the tail supremum is simplified as sub n equal 1 over n. But now notice something important. As n goes infinity, 1 over n approach 0. Therefore, the lim superior is also 0. Now let's look at the tail infimum. This time we ask the opposite question. If we go farther and farther out in the sequence, what is the smallest value we can still see? But notice something subtle here. The sequence keeps decreasing toward 0, yet it never actually reaches 0. So inside every tail, there is no smallest term. The number just gets closer and closer to 0 forever. That means the greatest lower bound of the tail is 0. So I sub n equals 0. Therefore, the limit inferior is also 0. At the beginning, limit superior and limit inferior were introduced to study sequences that failed to converge. They were supposed to help us understand oscillation and irregular behavior. but now something surprise is happening. These same ideas also seem to describe convergent sequence perfectly. In this example, both the upper behavior and the lower behavior eventually collapse to the same number. And that suggests something deeper may be true about convergence itself. This example is revealing something important. When a sequence converges, the upper behavior and lower behavior can no longer stay separated. Eventually, they are forced to collapse into the same value. In other words, the sequence stops oscillating in the long run, and mathematically, that is actually what this equation is saying: lim sup equal lim inf. So maybe convergence is not just about approaching a number. Maybe convergence means that the upper and lower behavior eventually become identical. So now we arrive at a new idea. Maybe convergence itself can be completely rewritten using lim superior and lim inferior. Instead of asking, does the sequence approach a number? We can ask, do the upper and lower behavior eventually become the same? And this leads to the following statement: x sub n approach x if only if lim sup equal lim inf and equal x. And today, this becomes our main theorem. Before proving the theorem, we need one classical result from analyze. It is called the Squeeze Lemma. The idea is actually very intuitive. If a sequence is trapped between two other sequences, and both sides approach the same limit, then the middle sequence has nowhere else to go. It is forced to approach that same limit as well, and this lemma will become the key tool in our proof. Now let's state the lemma more formally. Suppose we have this sequence A sub n, B sub n, C sub n, and assume the middle sequence is always trapped between the order 2, A sub n less than or equal to B sub n, and B sub n less than or equal to C sub n. At the same time, both outer sequences converge to some number L. So left side approach L, and the right side also approaches L. Then the middle sequence cannot behave differently. It is squeezed tighter and tighter toward the same limit. Therefore, B sub n approach L. This is Squeeze Lemma. This lemma is actually very geometric. Imagine the sequence B sub n trying to move around, but it is trapped between A sub n and C sub n. And now both sides start collapsing toward the same limit L. So the space available for B sub n becomes smaller and smaller. Eventually, there is nowhere left for the sequence to escape. It is forced to approach L as well. That is entire intuition behind the Squeeze Lemma. We are now ready for the main theorem of today's lecture. This theorem completely changed how we think about convergence. Traditionally, we define convergence using the epsilon n definition. We ask whether the sequence eventually stays arbitrarily close to some number x. But this theorem tells us something remarkable. Convergence can also be described using limit superior and limit inferior. More precisely, a sequence converges to x if only if its eventual upper behavior and eventual lower behavior both collapse to the same value x. In other words, lim sup equal lim inf equal x. So, convergence is no longer just getting close to a number. It is also the disappearance of long-term oscillations. Up to this point, this is probably the definition of convergence you already know. We say a sequence converges to X if eventually all the terms of the sequence stay arbitrarily close to X. More formally, no matter how small an error epsilon you choose, we can always go far enough out in the sequence so that every later term stays within that distance from X. This is a classical epsilon n definition of convergence. It describes convergence using distance and approximation. But now we can represent convergence in a completely different way. Instead of thinking about distance, we can think about long-term behavior. Every sequence has an eventual upper behavior described by the limit superior and an eventual lower behavior described by the limit inferior. If these two behaviors remain separated, the sequence still oscillates in some sense. But when they finally become identical, the oscillation disappears, and at the moment, the sequence converges. So convergence can be viewed as the collapse of the upper and lower behavior into the same value. Let's step back and look at the bigger picture. Traditionally, limits are used to describe convergence. We ask, does the sequence eventually approach some number x? But limit superior and limit inferior are doing something more general. They describe the long-term behavior of the sequence, even when the sequence fails to converge. So, unlike ordinary limits, this quantity still exists for oscillating or irregular sequence. In some sense, lim sup checks the eventual upper tendency, while lim inf checks the eventual lower tendency. And when these two finally meet, convergence appears. And this leads to the central idea of today's lecture. If the limit superior and limit inferior eventually become the same, then the sequence can no longer oscillate. There is no gap left between the upper behavior and the lower behavior, so the sequence is forced to settle down, and therefore it converges. In this way, convergence can be interpreted as the moment when the upper and lower behavior collapse into one another, or more simply, when the upper behavior equals the lower behavior, convergence appears.